welcome. I am very happy today that we can have this event here. It is an event in a series of presidency events. So we are very happy that we can be in Helsinki because this semester there is the Finnish Presidency of the Council of the European Union. We are extremely thankful to our colleagues from the organizing committee, the local organizers who have done a heroic job trying to put and piece different pieces together. And we are very thankful to the Academy of Finland, who is represented here by the Vice President, Mr. Ossi Malmberg, today. This is because it's great to meet, to learn what are all the developments that we have. We have a very high-level representation from the European Commission and from several member states. So today we are going to learn about developments in and outside of the flagship, what is coming even beyond the flagship in Horizon Europe, in the Digital Europe program, with new initiatives. We will have the possibility to learn about the situation today, to hear about a high-level debate this afternoon, different updates, and tomorrow we are going to have, at the venue near the university, the possibility to discuss in the community, to have feedback and to develop together a vision for the future. And we have a very tight schedule today. So this is why we are starting essentially without delay, and this is why I am also almost finishing my introductory speech, because I would be killed by Lydia and Alina, our organizers who took care of the badges, if I would not tell you that you have to turn your badge. You do not have to bug them. Where is the agenda? You turn your badge, and you make a picture with a barcode reader, and you will be able to download the agenda. Okay. But now the director of DG Connect shows me that he does not have this barcode, which may create some serious issues for future funding of our initiative. No, jokes apart, those of you who are so lucky to have the barcode behind, they can download the agenda and maybe provide it to Dr. Skordas, who might make a good use of it. So sorry, Thomas, for that. Thanks for everybody. And Mr. Malmberg, please join me on the podium. And thank you for being here and for welcoming us.
Ladies and gentlemen, on behalf of the Academy of Finland, I warmly welcome you to this Quantum Flagship event of the Finnish Presidency. And because you have another name in your agenda, I need to say I needed to replace Professor Heikki Manila with a very short notice. I need to also say in front of this distinguished audience that I'm not a scientist, I'm an administrator. But that only works for your benefit, because my welcoming words are definitely shorter than my Professor Manil's would be. And being an administrator, my colleagues say that is very close to human being. The theme of this event, it's extremely interesting, and this scientific area develops very quickly, and a lot of interesting things are happening at the moment. In Finland, we are very happy to see this large European collaboration working well, and also happy to see that there are excellent research groups in this area from Finland. For example, one of our centers of excellence in this field. Now, being an administrator, I will refrain of commenting on science, but some general remarks on the more organizational level are perhaps useful. There are three things crossing my mind thinking about this topic. Firstly, the role of European collaboration. Secondly, importance of infrastructures. And thirdly, the relationship of research, education, and the many-sided impact of science. Thinking about cooperation, I think that collaboration internationally and European cooperation is facing many challenges today. I hope that you forget your mobile devices and don't look too much about the Brexit deal, but concentrate on what we have on the agenda here today. In the field of science, I think we have very many splendid examples of fruitful cooperation in Europe and also internationally, and we are very happy about this success in scientific cooperation. This EU Quantum Flagship is an excellent example of European scientific cooperation. It connects the leading actors in this area, lots of excellent groups, and it is supported by the ERANET co-fund in quantum technologies. This area is such that cooperation is must. It has to be. From the point of view of science, and well, again, as an administrator, I could also say that alone we don't have the money. So cooperation is what we need to have. And from this angle of Europe being in Finland, cooperation for us is also a must. Nobody comes here for the climate. So having something interesting to work with all nations, other European countries, is very important to us, and we are hoping that also for you. And the role of excellence and wide cooperation is clearly visible here. And looking at the list of speakers and list of participants, I can sense excellence here present. On research infrastructures, they are very important here. They might be not all as large as, for example, CERN, but they are large in general, and they need to be large, and also funding is needed for this purpose. They are essential and absolutely necessary. Thirdly, research, education, innovation, and other types of impact go together. Excellent research, high-quality education, and innovation activities create a positive cycle, and each benefits from the others. And during this event and after this, I'm hoping that this enthusiasm, which I can sense here present, will also share and be distributed to Finnish other parties to grow further. I would like to especially welcome Mr. Khalil Ruhana, Deputy Director General for Communications, Networks, Content and Technology from the European Commission, and Dr. Jürgen Blünack, Chair of the Quantum Flagship Strategic Advisory Board. Again, ladies and gentlemen, welcome to this event. I wish you a very fruitful event, and looking at you and looking at the agenda, I'm convinced that it will be very fruitful. Thank you, and welcome again.
Very good. Thanks a lot for this introduction, which sets a joyful tone for today. We have many joyful things and to happen. And first of all, of course, we wanted to hear from the European Commission. And so Deputy Director General Khalil Ruhana from DG Connect agreed to join us here. And so we are going to hear from him what is coming next. And he is speaking about the future beyond the flagship initiative. So it is something which concerns every one of us very closely. Thanks a lot for joining us. Please, the floor is yours.
Thank you, Thomas. Thank you for inviting us and associating us to this event, and thanks for the Finnish Presidency for organizing it. It's a real pleasure to be here with you. So I'm Khalil Ruhana, I'm the Deputy Director General in DG Connect. What I'll be presenting to you is how we see quantum technology evolving in the future and what types of actions we envisage in this area. Works?
Now it works.
Very good.
If you
Thank
use
you.
that, then it works.
Okay. We do that always, you know. We create problems here to tell you that we need more money for research, development, and innovation to make the technology better. I'll brief you a bit about what we're having in mind and share with you some of the ideas for the future. As you'll see, quantum technologies is one of the key priority areas for the Commission, but also for the EU as a whole, and it has developed and shaped up as a strategic area where Europe has to make all the efforts to be in the lead, to make sure that we are the first and the first in making the best out of this technology in different sectors, be it for our industry, be it for our societal challenges, be it for our security, our strategic interest in the future. Today, if you look at the policy priorities that were announced by the new president-elect of the Commission, first of all, digital is one of the 6 priorities, 6 main priorities, and the digital means succeeding in making the digital transformation a big success for Europe, making sure that digital transformation brings benefits to all our economy and society. But within that digital transformation and the digital priority of the Commission, the President-elect was very precise as well, saying that we need to have technology sovereignty. We need to ensure that we have the key elements in Europe of the digital supply chain that are essential for our economy, our society, our strategic interest, our security, our defense of the future. And if you look at the technologies that she highlighted as key technologies for the future, is to see quantum as one of the key technologies. It's the first time that I see quantum in a policy declaration of the Commission at that level. So I think now we're close to make quantum applicable across all sectors. And I think it is not only about hype, it's about real applications and real benefits that it can bring. So that's to address the context and where we're talking. So we're talking technology sovereignty, we're talking about digital transformation of our economy and society, and we're talking about quantum technologies as a whole as a key pillar to make that digital transformation a success. Where is Europe today in quantum? And I can just summarize this very quickly. We have assets, of course, in quantum physics. We have the foundation of quantum physics coming from Europe, not only in previous centuries, but also very recently, as we know. We have also we have been investing in Europe since now, I'll say, I mean, if I remember well, the first time I came to the Commission in 1993 already, we had the first projects on quantum technology, moving from quantum physics to technology at that time. But since 1999, we have a very precise work program on quantum in the future emerging technologies areas. And so far, we have had close to €500 million invested from the EU side on quantum technologies. And if I sum up, there was a very good study done by our Dutch colleagues on all the investment that is done across Europe on quantum physics to quantum technology, science to technology. And we're close to €400 million a year that is invested in Europe in this area. It's important, this figure, because we hear a lot about the investment done in China, investment done in the US. But if you take together all what is done in Europe, we're above the investments done elsewhere. But the problem is that this investment is fragmented. It was very fragmented. And you have programs that are here 3 million, 4 million, 5 million in some member states, fragmented across the institutions. That's why we think that we have what we have managed to do together. This is the subject of our meeting today, i.e. develop a flagship that can federate that effort, that can help us all together support a common agenda established by the academic community. It's so essential. It's so essential to lead for the future. We have, of course, world top level research institutes and labs. These are our assets. Let's build on them. That's where the Quantum Flagship comes in our strategy, as I mentioned. Common research agenda, €1 billion over 10 years. So it shows the ambitions. Established by academia with industry. It's now time that we start thinking about bringing the quantum to the market and acting in order to bring it to the market. Public support from EU member states. And we saw member states already aligning their agendas to the agenda established by the flagship, and from basic research to industrial application. We already started with €130 million in 2018 of investment with 20 projects dealing with 4 areas: quantum communication, quantum computing, quantum simulation, quantum sensing and metrology. I'm sure you're familiar with this, so I will not elaborate on that too much. What is interesting is that in addition to the important work that we're doing on basic research, and we need to continue doing it, a lot needs to be done still, we know, in this technology. But we start to have industry interested. That's 30% of industry, mainly SMEs. I could tell you that 4 years ago, we tried to have, with the colleagues here, with Thomas and several of the colleagues, to have workshops with industry on quantum. We called industry all around, and it was very difficult, very hard to find any industrialist in Europe who would be interested in this field. Today, it's the opposite. Industry is knocking on the door and saying, can you involve us in quantum? So things have changed. I think it shows the maturity of the technology, but it also shows the interest in what Europe has, which is a top-class academic community in this field. So we have example of projects. What's interesting is that we start having now 2 platforms of quantum computers. You'll see that they'll be very important for us for the future, and with different technology. And we're tackling most of the areas. And so there are more projects that are, let's say, a sufficient size to integrate different concepts into a realization and achievement. And there are longer-term projects that we need still to support. And that balance is extremely important that we need to maintain. So, but we're not the only ones investing in quantum, as we know. Quantum worldwide, and I don't need to tell you about how important that is in US and China, in Japan, Canada. Large investments in the private sector. We hear about them in the press. I would have liked to have more of the industrial investment in the press coming from Europe as well, or from European companies. I hope it will come. Some of them are happening. There are large investments done by European industry, but we don't see them in the press a lot. And that's something also Europe is not good at, i.e. showing what we can do. So large-scale deployment projects, and that's very interesting. The Chinese quantum key distribution, large-scale, I would say it's more than experimentation, it's real deployment with hundreds of millions of euros behind it. The Chinese, when we read about this Chinese, I thought that China has invented the quantum key distribution, or they're using technology made in China. In fact, no, they're using technology coming from Europe. So we're very good. We developed the technology, but first deployment are happening in China. I need to be careful about this. So the defense programs in the US, of course, we know about their projects in this field as well. 4 key pillars for the future. That was where we are. Our assets, the competition worldwide, the investments that are done in this field. So what is it that we're going to do about it for the future? How can we build off what we have achieved together? The programs that we have been supporting at EU level in the member states. This wonderful knowledge that we have around Europe. The flagship that now help us federate the effort and align our efforts towards common goals. How can we build on that for the future? And we see the future with a comprehensive strategy that we need to put in place. 4 key pillars: reinforce R&D effort. We will continue. The flagship will be a very important part of that effort from the EU side. And I hope that that will enable us to continue aligning our strategies in Europe. But we also have quantum now as a key technology in the more industrial part of our Horizon Europe, in the digital industry and space cluster, and you'll see that later. And quantum application, other clusters in cybersecurity, for example, but also in health. You'll see that in what we're foreseeing in terms of research and development. And we see Horizon Europe playing a very important role, of course, there. But just to also come back to insist on this, the European effort, if it's done by its own, will not be sufficient. That's why the role of the flagship as a federating effort and work together with the member states and with the private sector is very, very important. If we count only on the European effort, dissociated from the rest in all our areas, and in particular in this area, we will be subcritical and we will not achieve the leadership we want. That's for the working together is very important. But we need also to start building the quantum capacities and infrastructure, quantum computing, quantum communication infrastructure, We have a program that we have proposed, and that is a new program, the Digital Europe program, that is exactly focusing on building capacities. We want to have the first computers in Europe, the first quantum computers in Europe, and make them available to all innovators, to all engineers. It's extremely important. That program, Digital Europe program, will enable us to do so. We want also to be the first mover in deploying quantum communication infrastructure with the technology that is done in Europe. That's the Digital Europe program. It's about Europe being first mover in making the best out of the technology and building the capacity, acquiring these capacities. It's acquiring them and having them available, deployed, and used. And we need to widespread the use of quantum across industries. We have developed concepts like digital innovation hubs that bring latest technology to all industries. I would like quantum also to be also available in some of our hubs for quantum for industries. And that's an effort that we need to do together to see how also we can bring quantum technologies to all sectors across the economy. Set up testing and experimentation facilities, very important. There as well, we have support in the Digital Europe program to do that. But we also need to work in cooperation and further our cooperation worldwide in this area. That means mainly, for the longer term research, but also for some deployment projects. We can work with international partners who would like to work with us in this field. And it's not the demands that are missing, which is good. I mean, it shows the sign of our strength. We have people knocking our door from international partners worldwide saying, can we cooperate in quantum? But then we need to make sure that that cooperation leads to a win-win situation with our trading partner. We're working hard on that as well. Quantum communication infrastructure, an example of what we can do. I mentioned quantum communication infrastructure. What can we do in order to make sure that we deploy this technology in Europe? That's part of the future types of projects that we can have. We're developing this. It's about Europe being a first mover. We're trying to see whether we can build a quantum key distribution infrastructure that has a satellite-based part and a terrestrial part. We're working together with ESA to see how can that be developed. And we launched a call to all member states who would like to join in with us on this. We have 10 member states already working together. I hope that more will come in order to see how we can deploy such an infrastructure across Europe. Co-investment will be from the EU, from the member states, from the EU side of a Digital Europe program to a large extent. And we have already a pilot project on quantum key distribution that is launched. It's around 40 million euro, I think, Thomas, isn't it? For testing the technology in real setting with partners coming from around Europe. That's the type of project to bring the technology to the market and Europe being a first mover. We're talking about investments that will be in hundreds of millions of euros. And you'll see where this can come from if we build it up all together. On quantum computing, our goal is to have hybrid computers already in the range of 23, 25 that are available all across Europe. We hope to be able to build on the 2 platforms that already started to be supported in the flagship. That I hope there will be other, more platforms coming, a 3rd platform probably, that would be more focused on the industrialization aspect as well. We would like in the future to scale up, test and deploy these platforms in the future. Also for deployment that would come from the TAB, while in research and development will come from Horizon Europe. We would like to involve industry as quickly as possible and to make this computing infrastructure available EU-wide. Build the ecosystem for programming, etc., and mainly support skills development. And also look at the application in the different areas. What I wanted to show here with these 2 examples is that we can combine our work that we do on research and development with investments in building the capacities, with investment in deploying the technologies across Europe. And that's what we have foreseen for the future. Research and development will continue. The flagship is already mentioned in the text of the framework program, that we continue supporting the flagships, and it will be cutting across the clusters in the pillar 2 of Horizon Europe. We have quantum computing, one of the applications of quantum under advanced computing. We have quantum under key digital technologies, where we'll support industrial projects in addition that are on different aspects of quantum applications, from communication to sensing to simulation, etc. We will have quantum also applied to cybersecurity. This can be feasible as well. And you can have quantum technologies applied also in the other areas like health, etc. And that comes in addition to the investment in science that will continue under the ERC and the future science pillar, as well as projects that could come bottom up under the European Innovation Council. This is how quantum is now present in the Horizon Europe proposal. Let's hope we get the budgets that we have put forward from the Commission side, and that we can support these areas. You could see that in addition to the flagship, we will have also important projects, I hope, that will be more collaborative between industry and academia. In the Digital Euro program, where we see quantum today, and high performance computing, if you look at the strategic orientations, draft strategic orientation for Digital Euro program, please have a look at them. And I'm saying this because I'm insisting on that, because I know your community is not familiar with Digital Euro program. Please have a look at that. Have a look at what we have foreseen in the strategic orientation. They're online. They're for consultation now. If you look at the high performance computing, you see hybrid. There you see possible quantum computers in the future. If you look at cybersecurity, you will see the proposal that we're doing on how to support the quantum communication infrastructure in the cybersecurity part. Okay. If you look at what we have foreseen for digital transformation, so for the widespread of technology, which is the third pillar in the Digital Euro program, you could see the possibility to build up testing and experimentation facilities to spread the technology all across Europe. That's also where we can support quantum, and we would like to support quantum, and the advanced digital skills. We know how skills are important, and advanced digital skills, is there more advanced than quantum? Then I think it's something also where we can support advanced digital skills. We're looking for supporting master degrees in these very important areas. We're also looking for shorter term upskilling in areas that will be really advanced. We would like Europe to be a first mover in adopting latest technology. Quantum is a latest technology. And we would like to have the skills, we would like to have the capacities, we would like to have the applications and testing and experimentation across Europe. We would like to support research and development to make sure that we keep among the leaders in this area. We do in Horizon Europe, and we would like also to apply it and to have our industry involved in it. This is if you look at, this is what we have foreseen as a comprehensive strategy, complementing with complementary financial instruments that we have proposed forward to the Council and Parliament, and with also the plans to work together with the member states, with the industry, with academia and with industry to make our effort successful. As a conclusion, I think this comprehensive strategy is essential now. It has to be ambitious, in line with our political priorities that I mentioned at the beginning. And we can do it if we pool our effort, if we build on our assets, and if we are also not only developing the technology, essential, not only be leaders in the science, but also first mover in applying it. And our flagship, as I mentioned before, is a key initiative to federate our efforts, and we need to make sure that we retain and attract the best skills to make sure. So all this is good. These are plans. You could see what we have put as proposal. But if they are not in line with what you think is important, we will fail. So please tell us. Please look at the strategic orientation for Horizon Europe. Look at the strategic orientations we have put for Digital Europe program. And tell us if we are on the right track. If not, tell us what else we need to do. Your support is essential. These are for you. So please help them make them a success. Thank you very much.
Thanks a lot. Well, maybe Khalil, do not leave us yet, because we are 13 minutes ahead of schedule. And this is perhaps a wonderful opportunity, if you do not mind, to solicit maybe some questions from the audience, which could be some feedback that you have asked. I mean, this is really serious, because this whole initiative has been based on the fact that the Commission is actually listening to what we are saying. Okay, so it was really a true thing in which we can really influence things. So please, look into these documents and through the coordination action give feedback. But maybe there are already pieces of feedback or questions now for Khalil.
Hey, great talk, thanks. Mikko Möttönen from Aalto University and VTT Finland. I wanted to maybe a little bit ask you to share your vision about the quantum computer infrastructure, which I believe is not as advanced as the quantum communications infrastructure. So what is the current sort of vision or different possibilities for that and the time scale?
Yeah, very good. First, let me say that Europe is not completely absent from this. We have already Europe-made simulated quantum computers that are on the market and that are, Aalto sells today and has machines with quantum simulated computing capacities in there. So we are in this loop. And you know that companies like Microsoft or Google, or they are teaming up with European research labs to be able to upgrade what they have as embryonic quantum computers. What we think is important is that we have quantum computers coming out of the flagship of these projects and additional projects deployed that are beyond 50 qubits by 23-24. This is our objective, and if you tell us it's feasible, we are, from the EU side, we will put all what we have as possibilities to make it happen. I can tell you it's a priority for us. But we would like these to be available to all Europeans, to build the whole ecosystem around it. We know how important it is strategically. We deal with cybersecurity. We know what will happen, once these 50 qubits will be applied for cryptography, for decrypting. We know what will happen, and this is why we're putting the quantum communication infrastructure on the table. So we're preparing for that. We know that if Europe does not master the quantum computing technology, we will be, in 5 years or 6 years from now, in big trouble. Not only for our industry, clear, but also for all other aspects related to our capacity to address our societal challenges, to our security, to our strategic interest. I cannot be clearer than this.
Thank you very much. Another question over here.
Hello, my name is Meri Helle from Summa Semiconductor at OneFab Finland. We are working with microelectronics manufacturing. And I attended an event in the US last summer, and I heard the talks about the Intel and IBM and others. And it is really a struggle you need probably new materials and new microelectronics manufacturing methods to fabricate the quantum circuits. And you can't do any computations without the actual microchips or the actual devices. So I think it's very important to have research infrastructures that can give access to companies and research groups of developing the new materials.
100%.
And we've been studying very carefully about the development of technology. And it usually takes 7 years to get when it leaves the lab or it leaves the research infrastructure, when the research phase is ready, it takes 7 years typically to get the manufacturing processes right, and also the design to match the manufacturing and then enter the market. So it takes really long time.
No, definitely agree. And one of the plans that we have is to have a network of testing and experimentation facilities for quantum chips. It is one of the I would say, project that will be in the pipeline. We can develop that in the Schlier program because we have the money to do the capacity. We hope to have the money to do the capacities building, but we can also support all the testing and experimentation from Horizon Europe using these capacities. We can, by complementing the two, we'd have the full scale. It's really what we have in mind. So if you have ideas how to build them, please tell us. Okay? Yeah.
Good morning. My name is Victor Land from QSoft in Amsterdam. In the Netherlands, we recently just finished the process of making a national agenda for quantum technologies to, coordinate a lot of stuff. And in your talk and on the slide, you used the word federate, which to me means putting control in one place. So could you elaborate on how that works?
Probably I shouldn't have used the word federate, and I know this. No, just, and I use it's the flagship that helps us federate the effort. And it's about co-investing or investing together or investing all of us in a common agenda. That's what I call federating the efforts. It's not about controlling. I think we learned in this area of digital, for those of you who are familiar with the work that we do in Excel or we do now in your HPC, what we have really learned together is that which is extremely important when we co-invest, be it with industry, be it with the member states, is to build a climate of trust where we trust each other, and then we spend time and even fighting in order to get what is our common interest. And we succeed if each of the member states, each of the industrial partners, each of the academic partners can find their interest in a European initiative. There is no European horizontal initiative that is for Martians, or I don't know for who, that will be unsidely controlled from Brussels. It would not work. What would work is that everyone feels a part of a common agenda. And that's what we're really working on. That's what we like with the flagship, that it's built by you, the agenda. I hope it's the case. And then we come and support it as a federated effort, if you want. That's the word. But I try to find another word. If federated is create fears.
So maybe we have time for a last question, please.
I'm Liviu Zerbo from Romania. And the question is related to the effectiveness of the flagship. So you came up with a sum, and you are giving it to us, right? And based on your experience with other flagship, do you have any estimate of how many people or how many more money you will need to actually get in front of our competition from US and China?
Excellent work, really. And, exactly. Something we look at very carefully. Yeah, just say that in the flagship we can support today up to 5,000 researchers per year across Europe, you see. Up to 5,000, which is, I think, a big amount. If you compare it with the biggest corporate lab of the biggest company, we are in the same orders of magnitude, or even more. This is what we can do today, 5,000, for the best researchers in Europe. And our programs, in our normal, if you take the total amount that we have in the EU programs, today we can support between 35,000 and 40,000 of the world's best researchers in Europe. This is what we do. And this counts a lot. Because I know that people say, oh, they look at the money that these companies are putting, can you compete? If you look at the total amount that you can mobilize with EU initiatives, and if you add to that the amounts that the member states and the efforts that they are doing in this common agenda that you have established, it becomes sizable. It becomes sizable. If we all push in the same direction, it is sizable. If we are fragmented and we say fragmentation, what does it mean? we did this analysis with our joint research centers of who does what in Europe does research and development. Fragmentation means that we spend a lot of money, which was the case, but with very small teams, some big ones, of course, this makes us, but a lot of small teams who are just trying to catch up with the rest. And they just trying to catch up and keep the knowledge, keep knowledge to be in, but not to make a step change. If you want to make a step change, then size matters. That by, pooling the resources, by working together on a particular goal, looking for complementarity, you can make a step change. Otherwise, you will have a lot of fragmented effort. It would keep us, in the knowledge, keep the knowledge, but it will not enable us to make a step change. Step change is by pulling our effort together, we can make a step change. And this we could see in some of the big projects, or some even smaller projects, where you have the best teams working together. Sorry, it was long, but you asked a very good question.
Thank you very much, Khalil. Let's give him a round of applause for this. For this very engaged and beyond formal, but really, heartfelt presentation. So this is very important to get this kind of encouragement from so high up in the Commission. It was a privilege. It is a privilege to have you here. Another privilege we have in the flagship is to have someone who, well, now is a free man, as he likes to define himself, but also brings a very strong experience in managing large research infrastructures. Jürgen Mlinek was, before being today the chairman of the Strategic Advisory Board of the Quantum Flagship, among his many distinguished tasks in the past, he was president of the Helmholtz Association, the German Association of Research Centers and National Labs. And he is now, we are very happy that he is now leading the Strategic Advisory Board. We just had a very fruitful meeting, I would say. And he is going to talk to us about where do we stand today with the flagship. Thank you, Jürgen, and welcome here. Thank you very much. Thank you.
Okay. Thank you very much, Tommaso. Welcome to all of you. I want to talk a little bit about this flagship, being a little bit maybe more precise as what you have heard so far. There are some repetitions, but there is a saying, the father of rhetorics are pictures, but the mother of rhetorics is repetition. So it's always good, if you repeat the important messages. Okay, now this is a first picture showing an ion, a single ion in a trap. Now, why do I show this? When we talk about quantum technologies, we are talking about the second quantum revolution. Now, I'm an experimental physicist by training. Quantum science is well known for some time. We have devices, bulk materials based on quantum phenomena, the transistor, NMR, the laser, GPS, and so forth. So many devices that are now used as consumer goods. And it's always, I think, very instructive to remember former times. I like James Bond movies. And my favorite James Bond movie is Goldfinger. And in Goldfinger, Sean Connery is driving with an Aston Martin in the Alps, having a GPS system. This was in the 60s, late 60s, early 70s. The laser was already invented. And he sees where he is. And everybody thought, come on, that's fiction. This will never happen, that in your car you see where you are. And now everybody has it. So we need some kind of fantasy. I'm showing this also because, for me, the second quantum revolution is also really related not to a change in quantum science, but to an advancement in technology. We can now create, we can manipulate, we can detect single quantum entities. Ions, photons, atoms, whatever. And this is just one example. And by the way, this picture has been taken with the camera of a mobile phone. Can you imagine, 20 years ago, take the image of a single ion fluorescing with the camera of a mobile phone that you have in your pocket, you take it out and you take the picture of the single ion? No way. No way. Now, this is, let's say, the introduction to this graph, which shows this Gardner hype cycle. And as you can see, there is an innovation trigger. There is a peak of inflated expectations. Maybe we are there at the moment. Then there is the stroke of disillusionment. Then the slope of enlightenment, and at the end, the plateau of productivity. And you know, when we talk about quantum technologies and especially quantum computing, also we as scientists, we have to be careful. We have to be, of course, ambitious, but we also have to be realistic. We should promise what at the end we are also able to deliver, because otherwise there will be a big, not only disillusionment, but also disappointment. And that's no good. That's no good for science. That's no good for politics. The Quantum Flagship, what's the vision? The vision is, you know, leadership, scientific leadership, kickstart a competitive European quantum industry, and make Europe attractive for innovation and investment. This is very important, and this has been debated a lot at the beginning of the flagship. This is not a flagship on basic research. There are many programs, and if I take the European approach, like the European Research Council, where money is available also for individual research, mainly at the frontier of science, basic science, new discoveries, fine. But here, the idea from the very beginning, and that's why it's on quantum technologies, it is on wealth creation at the end, using science, using innovation, but creating wealth, improve and maintain our standard of living, and create new jobs. That's the story. And for many people, also in the scientific community, of course, this is something where sometimes they are not very comfortable with. Because this wealth creation aspect is not an aspect, at least not in, you know, some of the European countries, and I would even include Germany in there, that is really on the radar of scientists. I'm not talking about people in companies. Okay. Now, timeline of the Quantum Flagship, where are we? We started with the ramp-up phase, which will last to 2021, and then we come into the phase 7 years of full implementation. And as we have already heard, it's a 1 billion euro activity, but careful, only but 500 million come from Brussels, but the other 500 million has to come from the member states. And nobody in Brussels can force the member states to contribute their share. Now, if I take Finland, 5 million inhabitants out of what, 400 million or so, it's a 1% effort. So you should at least invest 5 million euros into the quantum business. Hopefully more, because you are one of the innovation leaders in Europe. You know, there is this innovation score card, and Finland is always among the top 4 or 5. Congratulations, by the way. Germany comes not much later, but you know, Finland is ahead. It's great. So the 500 million has to come in addition, and I think This is something that we, from the scientific community in the different countries, really have to work on. We have to convince our nations, our politicians, you know, our members of parliament and so forth, that this is really important and something where we should go for. Now, in the ramp-up phase, 130 million for 3 years, there were a lot of proposals, more proposals, of course, than could be funded at the end. In quantum communication, 4 projects at the end were supported. In quantum simulation, 2 projects. In quantum sensing and metrology, 4 projects. In quantum computing, 2 projects. And in basic science, 7 projects. And I don't want to go into the details here, but that's the distribution of the funded project. And as a matter of fact, the acceptance rate in basic science was lowest, which was no surprise because, as I said, many also colleagues from the scientific community thought, well, we should submit, you know, a proposal as we do it with the DFG or the Science Foundation that we have in our national countries. But here, from the very beginning, one prerequisite was that the private sector companies should be included. The strategic research agenda is composed of 4 pillars, no surprise at the end. We thought in our committee what to do with software theory, quantum algorithms, what to do with engineering and control, and education and training, and we said this should be cross-cutting activities. Education and training, and this we discussed also today, should include also train people, especially the next generation, in becoming more entrepreneurial. Because if we want to create wealth and jobs at the end, we need, you know, I mean, companies who are interested in going into that direction. And the best is create new companies, maybe develop them even into unicorns, so that a completely new branch of industry can evolve. That's something that not so much is related to money and funding, it's more a mindset question. I think, you know, we have to become more entrepreneurial in Europe in general. That's different in other countries and definitely something that we have to work on. Now, this morning, as Tommaso already said, we updated our research agenda. That's work in progress. We will be done in the next couple of weeks and then send the research agenda to the Commission. And I think this will be the basis then for the call for the full phase. So we have done essentially our homework. Of course, there are some issues that still have to be addressed. Platforms and thematic areas, performance of the flagship. And let me say a few words on these 2 topics here. Platforms also have to do with this question of infrastructure, which was brought up also here in the discussion. And of course, if we compare, and I'll come back to that later on with another slide, Europe with other regions of the world, and that's essentially as competitors, the US on one hand and China on the other hand. In the US, infrastructure at the moment is financed by the private sector, by internet companies and semiconductor companies like Microsoft, Google, Intel, Honeywell, IBM, and so forth. In China, it's more the state that has some unlimited resources of money. The Chinese somewhere must have a money printing machine. I would really like to know where, but that's somehow, you know, the general feeling, unlimited resources. And the question is, we in Europe, what can we offer to stay competitive. And as our colleague Maria Stello from Italy said this morning, we have a high-quality research infrastructure in Europe. We have a National Bureau of Standards. We have national labs which are very strong and can definitely be used to set up research infrastructure that is competitive with the rest of the world. We just have to do it. We just have to do it. And we have to get our act together in the sense of looking as on Europe as a whole and not, you know, in these narrow national perspectives. Okay. Europe's commitment from vision to reality. As you can see here, there are different elements. There's the Quantum Flagship, there's Quantera, there are these infrastructure issues that I was just mentioning. And the ultimate goal is the quantum internet, you know, where you have computers, simulators, sensors, and then links via space or fibers and so forth. And this all over Europe. As a matter of fact, I was surprised by the activity in Finland on this map. I don't know whether this was made on purpose or whether it's really, but again, congratulations. Okay, now international cooperation and competition. As I said, there is competition mainly from the US and from China in those fields. And I was really amazed when I realized a couple of years ago that the major drivers, especially in the field of quantum computing in the US, were companies. And you know, what also surprised me was when I was talking to some of the colleagues who are now working for companies like Google and were at universities beforehand, told me they were never as free as they are now to do what they would like to do. And that's somehow strange. We should really think about it. How come that people who are working with companies like Google, Microsoft, Facebook, and so forth now go there and have the feeling we are freer to do the research that we really think we should do because we consider it important and really at the frontier, and not stay in public institutions? Something is unbalanced here. We don't have these opportunities in Europe. The situation in China is different. As I said, there, you know, you have a strategy. The Chinese government has a strategy. And if they sit together from the Polit Committee in the evening, the next morning, action. There is no debate over years whether to do something or not. Is action just the next day? So different dynamics, and we Europeans somehow have to deal with it. And there is a need, that's why I'm saying this, there is a need of urgency. Some examples: international cooperation, but also competition. This is the gravitational wave detector, the laser antenna in Hanford, LIGO, which detected for the first time gravitational waves in September 2015. Now, why do I show this picture? It's a 3-kilometer long interferometer arm, and the message here is, and I wasn't aware of this as a matter of fact, that every decade the sensitivity of an optical interferometer is increased by a factor of 10. Now think back to the first experiments with the Michelson interferometer that Michelson did in the 1880s and so forth. Now the sensitivity is in delta L over L 10 to the minus 22, 23. And the question, of course, is will this go on? And my colleagues from gravitational wave detection, they are saying it will go on. And it will go on, for example, because the lasers will use squeezed light, non-classical light. And I myself, I was working on the creation of squeezed light in the 90s using optical parametric oscillators. And you know, in the last paragraph, as a scientist, you always say a few words on the brightness of future. You know, the future is always bright in the last paragraph of a publication. And my message was, squeezed light will be one time used in interferometers for gravitational wave detection. Did I believe it? But now again, it's reality. Now it's reality. And you know, if you increase the sensitivity by a factor of 2 to 3, you increase the number of events by a factor of 10. And a couple of years ago, people were happy to have one cosmic event that gives a gravitational wave detection once per year. Now they have a few events per week. It's fantastic. And again, it's an example for, you know, pushing technologies, and we should be really optimistic that also quantum technologies will help in improving all this. International competition, cooperation, of course, but also competition. This is this press release. I don't know whether the paper is out by now from Google on this 50 qubit superconducting machine where they are saying that they showed quantum supremacy. I was talking the day after the first press release to people from IBM, and there the story sounds completely different. You know, if you talk to people from IBM, they have a different understanding of quantum supremacy than the Google guys. But anyhow, this is our competition, and we have really get our act together to set up something like this. And the question is, again, should we buy one of the D-Wave machines for, I don't know, $20 or $30 million? Or should we set up something by ourselves, play around with it, put it into the cloud, give the possibility to combine it with high-performance computing and play our games ourselves? These are questions that we have to address, that we have to honestly answer also in the framework of this flagship. Companies. These are companies that are somehow involved in quantum technologies. And again, we have a serious discussion among us and also together with the Commission, which company qualifies as a European company in the sense that, you know, it can be part of the European flagship. If IBM is part of it, does this mean that people from Zurich Rüschlikon profit from all the knowledge within the European flagship, but also tell us what is going on in IBM Yorktown Heights and IBM Almaden? The same is true for Huawei, the same is true for Toshiba and so forth. Besides this question of, you know, patents and intellectual property rights and so forth, questions that we have to address and where we have to come up with some kind of, you know, rules so that we know who can be part of it, who not. And I think this is really necessary also not only for us, but also for the companies being involved. We need, I think, a broader basis for companies being part of it. Again, this was something that we discussed at length this morning. How can we do that? And in the US, and they are always very inventive in this respect, in the US they have set up something that they call Quantum Economic Development Consortium. It's an initiative originally started by the Department of Energy. they gave it to the NIST, their National Bureau of Standards, together with Stanford Research Institute. And here, companies come together that not only work on quantum, but that are also working on technologies that we would call enabling technologies for quantum applications, like cryogenics, like optical fibers, like lasers, like microwave amplifiers, and so forth. And if we do this, and we should do this, I think, also in Europe, and I think that the Commission will invite also the industry side rather soon, also very, very broadly, to discuss these type of questions, then I think there is more momentum also from the private sector, because the basis is much broader than just taking those few companies in Europe that are really working on, let's say, topics like quantum computing. So that's it. I think it's a great, initiative, this flagship. There is always the discussion, probably also in a country like Finland, at least we have it in Germany, do we need these moonshot projects? Do we need these men on the moon projects? Or isn't it better to give the money to individuals? Because at the end, people count, fine. People count, that's true. But sometimes you also need critical mass to achieve something that an individual alone cannot achieve. And I think if we succeed at the European level to really do this, then there is a realistic chance to really be again at the forefront of these developments. Thank you very much for your attention.
Thanks a lot, Jürgen. We may have time for perhaps one question to Jürgen Mlinek, if there is any. I do not see questions. Then, oh, there is a question.
So what is the main problem today to solve in quantum computing to have a breakthrough?
Well, the question here is, what do you understand as a breakthrough? Is it that with one or two examples you really show what some people call this quantum supremacy, that you can, solve a problem that even on a high-performance computer would take years to solve, even if the problem is completely irrelevant to applications? Is this a breakthrough? Or is the real breakthrough if you can somehow show that with quantum computing you can eavesdrop the most secure communication channels that exist at the moment? Very difficult to answer. Which technology is the right technology? I didn't dig into that. Is it one of those technologies which at the moment are at the forefront, let's say, also of engineering, like ions in a trap or superconducting qubits or semiconductors? Maybe these are these topological states which so far haven't really been observed experimentally, but if so, they are easily scalable and so forth. So the question, what is a real breakthrough here, is not easy to answer. It's really not easy to answer. I would say if you can come up with some system 50 to 100 qubits and really make it work, that I would consider a breakthrough in this area, because then you are factor 1 to 100, larger than what has been shown as a principle, as a first-hand principle some years ago.
Thank you very much. So, I guess that we are ready for the Finnish part of our day, in the sense that we are finished with the European part, let's say the first introductory presentations, and now we would like really to focus on what is going on in this country, which is hosting us today. And we would like to see this on 3 different perspectives: the scientific, the technological, and the industry perspective. And for the scientific talk, we have 2 colleagues from the universities of Aalto and Turku. And those are Jukka Pekkola and Sabrina Maniscalco, whom I asked to join me here on the stage. And they are going to talk to us about quantum technologies in Finland and looking towards the future. So thank you very much. And the floor is yours, if it works.
Maybe we have to connect it to this one, obviously. Let me just do it. Can I remove it? I know it works. If we are all here today, it's because we believe in a quantum future. This is a future in which the deepest and most subtle aspects and properties of the constituents of the universe, those aspects that make quantum theory so mesmerizing and unique, will be the drivers of a new technological era. We believe, indeed, that technologies based on quantum effects will lead to breakthrough in what are the most challenging, the most important problems of modern society, such as environmental challenges, the global energy challenge, the world health challenge. We believe that this will happen, and we believe that this is in our hands. Here in Finland, we have started a Center of Excellence on Quantum Technologies funded by the Academy of Finland, and this builds on our strengths and tradition. We have the aim of actually exploring new creative and multidisciplinary pathways to education and to research. And we also have a very deep belief that in order to do so, we need to consider technological innovation and fundamental research as equally important. We think, indeed, that building a successful and sustainable ecosystem for quantum technologies requires strengthening on equal footing quantum industry and basic science. And of course, both of them must be supported by functional infrastructures. Finland, through national funding agency and through private foundations and our universities, shows commitment to support research positioned throughout this spectrum. The interaction, the cross-fertilization and cross-talk between scientific endeavors having different technology readiness levels must be considered a top priority, not only for the academic community, but also by policymakers and by the national funding agencies. If we want to implement a truly successful societal and technological education, however, we need also to focus our resources on education and outreach. This is because education and outreach must be the vital lymph to the second quantum revolution. It is our duty and responsibility not only to educate and to form the new generation of engineers and quantum scientists, but also to inform, involve, and engage in the scientific discussion policymakers and the general public. Finland has a very strong tradition, is very famous worldwide for the innovative education system, and we want to build on our strengths to create multidisciplinary pathways to form young scientists. In Aalto University, we have already since more than a year a bachelor program on quantum technologies. In Turku, we teach quantum programming with NISQ devices on the cloud. In Aalto University, we also have our first PhD student with a program joining the School of Arts and the School of Sciences, with a curriculum which ranges from quantum physics to public outreach to game development. And to show you the commitment that we have on public outreach, citizen science, and science for everyone, I invite you all to the Quantum Explorations exhibition that is in Dipoli, in Otaniemi, in our campus, and this is the official place where we will all go for the welcome reception tonight, this evening. I invite you to explore also the game room, where there are video games for both research and education in quantum physics.
Thank you, Sabrina. So I will try to give you a concrete snapshot overview of what is going on in Finland, because I think this is what you like to hear. So I'm representing the Center of Excellence on Quantum Technology Finland, which is funded by the Academy of Finland, partly, and for an 8-year period with a midterm review in the middle. This is kind of, as we heard, Finland is a small country, so this is something that where we focus on certain aspects of quantum technologies. And our center represents maybe half of the community working in quantum technologies. So why quantum technology in Finland, and why kind of quantum technology that we are talking about now? So we have a very strong and long research tradition in Finland on low temperature techniques and superconductivity. So the low temperature laboratory was founded in 1965 by academician Olli Lounasmaa, and the older ones of you for sure remember the world records that were produced by this laboratory. It developed, and it has been involved in European research infrastructure collaboration from the 90s. It has been within the Center of Excellence programs in Finland since 1995. And we have a national research infrastructure since 2009. So how has all this developed? In the early times, what was important was cryogenic techniques, superconductivity, superfluidity. So we kind of did basic science, quantum science in here in Finland. Later on, doing squids, the superconducting junctions, which are the predecessors of modern qubits, superconducting qubits, we worked on quantum metrology and also applying squids on, for example, in brain research, even commercially. In the middle 90s, in the early 2000s, we moved more into the nanoelectronics, quantum nanotransport, two-dimensional materials, and of course, to superconducting qubits. So it has been kind of a natural evolution towards quantum technology here. So about our team. So we have a team of 10 PIs in the Center of Excellence. And I just very briefly tell the expertise and how we are combined. So my own expertise is in quantum thermodynamics and quantum transport. And as I would say that kind of the heat dissipation, decoherence are something that join us somehow together in this team. Sabrina Maniscalco is an expert on open quantum systems. Pertti Hakonen is a long-term expert in superconducting circuits and also in two-dimensional materials. Tapio Ala-Nissilä is a theorist on open quantum systems. Mikko Möttönen is developing superconducting qubits and bolometers and commercializing them as well. Christian Flint on quantum transport, and Sorin Paraunu is a specialist in adiabatic quantum processes experimentally and quantum simulation. Chipei Sun is coming from the community of quantum, or say nanophotonics, so he's using two-dimensional materials for nanophotonics. Then we have two groups from VTT by Professor Mika Brunilainen and Dr. Visa Westeren, who are mainly focusing on the applications and really being in between the basic research on quantum technology and science towards the industrial applications. So they are like the device experts in this team. So how large is this group? So altogether in this center we have about 100 researchers or 110 researchers, out of which a number of university professors and several senior researchers. And we, of course, we educate a lot of experts to the field. Like currently, we have about 50 PhD students and many postdocs as well. So what about the funding of this unit? So as I said, we have been very fortunate since the beginning of last year to have this status of the Center of Excellence by Academy of Finland. And this gives us, of course, the possibility to focus on long-term projects. However, the academic funding itself is only a kind of a very small part of, not very small, but it's only a part of the funding. It's like 13% of the whole budget of the research groups that I mentioned here. So what is coming on top of that is naturally the strategic funding from our host institutes, universities, Aalto, Turku, and VTT, and then in general the own organization funding. We have also other academic funding which comes in form of research positions within the center. So altogether, of course, this Center of Excellence as such brings us the big push in this research. We have a lot of, we have research grants from European Union, which is about 1/5 of our funding, and this is in form of ERC project and also in this starting flagship projects. So this is how it all is formed. And what are the important things for success? Of course, excellence in research. In these very carefully chosen research areas, then of course we are in line with our university and institute strategies, and they are committed to support us. And then the one more thing which I will explain a little bit more at the end is the infrastructure, which is very important for this kind of a center, which is really focused on largely on experiments, although with a very strong theory component as well. So what are our current grand challenges which this kind of a long-term funding gives a possibility to? I mentioned that dissipation energy in quantum world is an important unifying theme in our center. So that's why we are developing detectors, ultrasensitive calorimeters, bolometers, which would eventually really be able to have a single quantum level resolution for in the microwave regime in superconducting circuits. This would open a lot of possibilities for basic science and naturally for applications as well. We are doing a lot of work on quantum control by tunable environments, which also relates to this same niche that we have here. So this is a theory and experiment combined effort with many groups involved. In both these things, many of the groups are involved. We are developing pilot quantum simulator and then also flying qubits in 2D materials in graphene. We are a new center. We have already some research highlights, and I just put these papers here just to give examples, because they show that we are doing both basic science, but also applying our research to different devices like this one here. And on top of everything, I should say that we have been able to generate industry to this country and internationally. And there will be a separate talk about this story about IQM, which originated from our Center of Excellence recently. And in a larger time frame, we have had quite a lot of success, as Professor Mlynek also mentioned, that that we have had in Finland quite a lot of industrial advancements in the field of, or at least tangentially in field of quantum technologies. Our flagship for many years has been Blueforce, which is an enabling, which is making the enabling technique for quantum computing by superconducting qubits, by making the platform, the cryostats for this research, and I believe many of you know about this success story. But there are many others, much smaller scale things, which IQM mentioned, but all these things, all these small companies have been originating from either this center of excellence or from the earlier center that we had. So I think now I just round up by telling about our infrastructures. So what we have here in the Helsinki area is a research infrastructure which is called Otanano. Otanano is a national research infrastructure for nanoscience and technology, and now we are focusing a lot on quantum technologies, and it is composed of three different subunits, which probably some of you will have an opportunity to see if you didn't see before. So one of them is a kind of a consorted clean room facility, which has the processing lines for quantum technology available. So for superconducting circuits, it's being developed for several years, and it is currently being upgraded, and also for two-dimensional materials. So this is within the campus, as well as the high-resolution nanomicroscopy and sample characterization also at the university. And then the third very important component is that we have the facilities for ultra low temperature. I mean, for doing this very low temperature research and applications using mainly the dilution refrigerators, also at high frequencies. So this is for the qubit measurements. So I think this is I conclude here and give the floor to Sabrina.
Yes, for the very final concluding remarks, summarizing a little bit about our Center of Excellence. And I summarize it with this slide because I think that our strength is in our diversity, in our inclusiveness, and in our open-mindedness, and also in our tradition. And most of all, it's in the realization that true scientific and technological innovation must come supporting both basic science and quantum industry equally through all the spectrum. Let us not forget the roots of European excellence in quantum technologies. And we hope to build together a sustainable quantum future. Thanks for listening.
Thank you very much. I think this is really an excellent message encompassing the whole of this sort of Finnish session, so thank you very much. Since there is two of you and we have half a minute, we have maybe time for half a question, one quarter question for each. So who has half a question, please? No one. About what? Okay.
Okay, it's a good one.
Okay, very good. So thanks again. And so thanks Jukka and Sabrina, and then we can move on to Antti Vasara, who is the CEO of VTT, the Finnish RTO, and he is going to give us the technology talk.
Thank you. Yep. Imagine doing that then with a quantum computer, that it will take a lot longer. Thank you. Very good afternoon from me as well. I'm Antti Vasara. I'm the CEO for VTT, and it's a very great pleasure seeing this group here in Helsinki. One of the positive benefits of the EU presidency. I want to talk about what we do in quantum technology, and of course everything is linked to our partners like Aalto and University of Turku and many of the companies. But first, I want to address the question a little bit also why we are doing these things. So let me start with a video.
Wednesday. The day after Tuesday. Not quite Thursday yet. And by the time the laundry's done, you can sense the world has spun just a little bit further, beyond repair. What a time to be alive. Then again, this may be an ordinary day, but so was every day before every breakthrough. The day before we beat smallpox, before we saw an atom for the first time, the day before the first bytes of data shot across the World Wide Web. Never have futures unfolded in front of us as they do right now. As we speak, we are discovering extraordinary antimicrobial compounds in ordinary berries, so our children may beat superbacteria with cures directly from our forests. And right at this moment, we are designing hyperspectral cameras for satellites that let us see emissions and fight climate change from space. Plans are coming together for cities that are full of energy but free from pollution. So instead of cars, our children may focus on driving their dreams. We are living through pivotal moments every second. What an amazing time to be alive.
So why do we talk about these things? We have clearly seen that as a research organization, we get easily boxed into the technology box. That we do some technology and kind of like let the engineers kind of like deal with that. But everything that we do has a purpose. But we need to make that connection then that what that purpose is and kind of like talk with the language that society understands. Everybody is now talking about climate change, resource efficiency, and these types of things, and for a very good reason. They are basically existential threats to humankind, and we can show that we can produce solutions that help mitigate those things and solve these things. But we need to be the ones making that bridge. But it's also then that we need to help society imagine that there can be also solutions. So not only talk about the hard facts, but also sort of waken their imagination to see the future. And this is especially where I think that quantum technology comes in, because this is very futuristic that we are talking about here. And sometimes it is even hard to get people interested because they think that it's so far out. So how do we bridge that and show that this is reality? We at VTT, we have 2,000 people roughly working for us, and our job is then turn those challenges into opportunities. We work across very many fields. So I could be also talking today about how to make food out of thin air, or how do we design with artificial intelligence. Actually, we design life, or we design artificial materials and these types of things. But today I'll focus on just one corner, which is then the work that we do around microelectronics, and especially then on quantum. I think that this is really an amazing time to be alive, like it said on the video, because we are now, at least for the first time during my lifetime, we are living through same type of pivotal moment like it must have been that when transistors were invented. Most people probably didn't even understand what they were. Most people didn't understand the consequences, but that was a huge jump in what society and mankind could achieve. And I strongly believe, and I think that I'm preaching to the choir here, that the quantum technology is going to do the same kind of leap. and this is sort of then where we need to be communicating then to our colleagues and the society at large then that the major breakthroughs in mankind always have been underpinned by some technological breakthrough. Agriculture had many things that now seem trivial, electricity, transistor, these things. There always been a jump, sort of a major leap coming out of there, of course combined with societal development. But equally impossible it has been then to imagine then the possibilities. I bet that the people who invented transistor did not think about Netflix or Twitter or all the things that are nowadays possible through the technology. We need to help make that imagination leap also for people. Now, of course, there is then the hard technology that needs to be developed, but unless we can justify the reason for these things, I'm a little bit afraid then that some of these things will be pushed aside. And that's why I was so delighted to hear from Halil Ruhana then the thinking that goes on in the Commission, that at least at the Commission level, the connection has been made between these technologies and what they can solve. But it is important then that we all support that message. Now, technology. We are at this breakthrough moment, of course. We have been for a far longer time in quantum 1.0, where we are utilizing the quantum effects in technology, and we don't even anymore notice then that we have lasers or GPS, not only in James Bond movies. And we are now moving then to the quantum 2.0 phase, that where we are actually then utilizing really quantum states and these types of things then in real circuits. As the previous presentations have already covered, then that there are many things going on, and of course quantum communication seems to be the first one to emerge in real life. So this is the one that's least science fiction at the moment, so this is going into implementation. Sensing and metrology similarly is an area then that where real things are happening, but maybe not as easily understandable by the general public. And of course, the promise of a quantum computer is somewhat clear, but of course, there we have the biggest steps to be taken. Now, where then a small organization like VTT with its partners here in Finland can make a difference. So we have of course been thinking a lot then that how to contribute when China is investing tens of billions of euros, even companies are investing billions of euros, and we are operating on a shoestring budget. So we need to be good in targeting then that where we make that dent in the universe. And of course, now I'll only cover then essentially kind of like then the superconducting technologies that are used in quantum. So I don't go into the other technologies, but it is important to realize then that many of the things which we have perfected on the microelectronics side are extremely relevant now for quantum technologies. We are at the stage that where microelectronics is very much geared for performance and price. So it's in the mass market situation, and all the huge operations that are out there are essentially run for that. If you look at the quantum ICT part, here the three most important things that we are looking for are performance, and then performance. And that requires more research orientation and essentially then ability to be able to customize, modify the processes on the go, and really kind of like target for that particular application. And that means then that much of the work that we do is more akin to doing high-end instrumentation rather than mass manufacturing. And for us, of course, the key tool is part of the Otanano infrastructure that Professor Pekola was mentioning. Then that we have our Micronova facilities, roughly 10 kilometers from here, close to the place that where the event tonight is. and where we have since 1997 had the clean room facilities for doing photonics, but also superconducting circuits. And when everybody else went for CMOS technologies and kind of like the mass market, we figured out that we will run out of money in a week, and kind of like before Intel blinks an eye. And that's why we need to find a different niche that where we are operating, and went then to technologies like our photonics platform that's using a 3-micron SOI platform to do things. And that's how we have been able to actually differentiate in a really nice way. In Finland, describing a little bit differently what also we saw in the previous presentation, then that there is an emerging ecosystem around universities, funders, companies. So in that sense, then that and spin-off companies like IQM that we'll hear next. So there is a business already starting to emerge, but way more can be done. We are overall as VTT extremely active in Horizon 2020. Proportional to our size, we are probably in the top 3 in performance there. But then things like Quantum Flagship are crucial for us to get then to do bigger things. And like the person from Academy of Finland was emphasizing a lot, collaboration is for us basically the most important thing. If we try to do things alone, we are not making any headway there. So some of the then I want to tell a little bit concrete examples of what we've been working on. So in the Quantum 1.0 era, we started already in the 80s. So like Professor Pekola was telling about the long heritage that we have around low temperature physics. One of the outcomes of that was the work that we started to do in the 80s around squids. So there have been these MEG machines with niobium-based squids utilized in production machines that we were manufacturing. Some of our stuff is out there in the space. So in the Athena project, we did squid-based multiplexers for the detector arrays. And then more recently, for example, Askella, which is doing terahertz imaging with the bolometers, and these are hopefully things that will change the way that we have to go through airport security in the hopefully not so distant future. On the Quantum 2.0 area, few examples from things that have emerged from the collaboration that we've done with Aalto. For example, this quantum circuits refrigerator, so that we can reset the qubits more easily and faster readout of then the qubits with these types of circuits. And these are then some of the technologies that have been the basis then for IQM and who are now commercializing then these in that spin-off. Then one area that what we are currently focusing on is around linked then into the scaling up of quantum computers. So on the in the classical microchips, nowadays these chips are very much 3D structures. So having very many layers there. In quantum chips at the moment, that's the issue, that they are still 2D structures, and all the error correction codes at the moment, the modern ones work in a basically a 2D lattice. And if you start stacking them, you easily destroy then the quantumness in there. So, but if you just use the 2D structures, at least what we've been looking at is then that limits then the number of qubits that you can have on the chip then into very low numbers, like 20 or so, which means then that you can't do anything significant. So you need to start be able to do also 3D structures in here. And we've been then starting to look at how to basically have still of course the qubits in one layer and then putting the readout chips on top of that. And this is part of obviously one of the initiatives that are under Quantum Flagship. So this is of course one of the areas that we do in collaboration in Open SuperQ. So our solution here, what we're working on is around the flip chip bonds and then through silicon vias, superconducting ones, and then utilizing then the work that we have been doing for quite a long time with parametric amplifiers, and that way being able to do very low noise solutions in there. And of course, these are also relevant then in the sensing and metrology side. So one of the things that was very recently published then was this record high sensitivity microwave detection around 20 zeptowatt or 10 zeptowatt resolution, which is 10 to minus 21. So low numbers. Scaling up then, of course, beyond this is that although we are now in the tens of qubits range, and maybe Google has this 50 qubit one, but we need to get into the millions, and very soon, kind of like the connectivity between the different, basically getting the connections out of the cryostats that we can't anymore fit physically all the cables that are required there. So we are looking into then how to use photonics and optical interfaces there, that creating basically new types of optical electrical interfaces that operate in the, of course, in the cryogenic area, but also then that maybe utilize technologies like single flux quantum processors that connect then into the quantum processors, and in that way then create chips that allow then to get way more information out from the millikelvin areas then into the room temperature areas. But the points that I wanted to share with you in this quick presentation is that we all share here the excitement around quantum, but it is our duty then to make rest of the world also excited about then that we are again living through the area that when sort of the era of new transistor. There is super good knowledge and expertise in quantum technology in Europe, but the competition is really hard. It is vital, like Halil Ruhana said, that we retain and develop that competence in Europe. And also then that this is not sci-fi. We have the excellence, now's the time to start building up this industry. And this is also something which is very unique, that you can be witnessing that the new industry really emerges. And the quantum industry is now being born. And think about, for example, mobile industry. Still in the 70s, nobody spoke about that one. It was tiny, and now it has grown into these tens and hundreds of billions of euros. And I believe strongly that we are seeing a similar type of thing here. And that's why this is so exciting. And for us, we aim to be one of the leading quantum microsystem foundries, if not only in Europe, but also in the world. So we want to collaborate and partner with you. So please talk to us. Thank you.
Very much. Looking at the watch, I see that we have time for another half question, which summed up with the previous half one, maybe gives one question. One question, anyone? Yes.
Do you feel that on the last slide you showed these three big items? Like, do you feel that the first one, how we connect to society, so to say, gets enough attention in
the
flagship?
Not at the moment. Right no, clearly
what
not.
should be done then? You
look suspicious there now. That I think that we need to make that connection, like also Sabrina in her presentation in the beginning said then, that we need to be talking about the challenge, the questions that require answers, and that's what the society is concerned about. And then it's our job to make the connection and explain then that why in some areas you require computing power which is totally beyond what we have at the moment. And that's the thing. We don't need to explain the details of quantum mechanics to people, but we need to make the connection then that there's a gigantic step change that needs to happen, unless or otherwise we won't find the answers. And that requires setting the context, explaining, and kind of like talking with the same language as the society does.
Thank you very much.
You.
So we finish this round of Finnish stuff with Jan Götz from IQM. And he has a title which is really kind of refreshing after all this depressing thinking about, oh my goodness, can we ever survive the Americans and all of that? Because his title is Shaping the Quantum Future from Europe. So this is really one prime example of the fact that, yes, we can compete. Yes, we can. Please.
A very nice introduction, and indeed this is our goal, is not to be a passive observer but really be active in this whole quantum field and be an active player in shaping the quantum future from Europe. So thank you the organizers for giving me the opportunity to talk here. I don't know where my slides are, but anyways, I think it was mentioned earlier that one of the wishes from the Commission is that there will be a company which is set up to build a 50-qubit quantum computer. Well, here we are. So this is exactly the goal for IQM, is to build a superconducting quantum computer. We are actually not only this, but we are a spin-out also from the flagship, or more the European funding scheme. I think the technology which is in here is not only the flagship because it's not so old, but it's more than 10 years of research done here in Helsinki, funded partly by the European Union. So this is really what is happening here in Finland. So on a global scale, we have heard this already quite some time today, the numbers that the US are investing a lot and China is investing a lot. And I just brought here this example. It's a recent Forbes article which also touches this topic on how do we create awareness, why are there not these kind of news in Europe, and I think we have to work very hard on this, and we are trying to do this. And of course this is a US article, and you don't have to share all the opinions which are in there, and I actually don't share everything which is written there, but it's worth to notice a few sentences. One is that China understands the strategic importance of quantum technology both to its economy and its military. So what we see is that really the decision makers are anticipating a huge disruption for economy. This is one thing, and I think this is why we are going here. On the other hand, we have to be aware that still a lot of funding comes from the military sources, and we shouldn't kind of be too childish with this one. But the main point is that really there is a strong motivation to invest in this, even there is not really a market yet, but just with the vision there will be a market, and when it's there, it's very important to be active. The other sentence I brought here is that, however, thanks to investments by our tech giants, IBM, Google, Microsoft, the US states has maintained its lead. And I'm not commenting here on the lead, but more on the fact that actually there are these very big companies like IBM, Google, Microsoft, who are active in this field. And this really shows that the decision makers in the very powerful companies, they are believing in this technology, and they are really willing to invest a lot of money into this technology. So the main message here is that quantum technologies will disrupt many fields of industry, and it will have an economic impact. And if we as a European society want to be part of it, then we should act now. And I think this kind of quantum flagship initiatives and these kind of events are very important to help this process growing and to be, as a European entity, much more active in this. And if you have been looking careful at the slide, you can see that down here in my browser, I was looking for the word Europe in this, and it's not mentioned in this article, which I don't think is justified, because we have such great technology here, especially on the academic side, and it is emerging into industry. The only fact is, it's not emerging into the big companies like Microsoft and so forth, but we see a lot of activity in startups, and I think what we have to do as Europe, we have to kind of push these activities and help the startups to grow more actively to be able to compete with the big ones. And I think this is very important if we want to be, on the long run, an active player in this story. And this is actually what we do with IQM. So we have put a lot of effort in not getting some money, but getting sufficient money to be able to compete with the big research teams in the US. So in July this year, we have announced a 11.45 million seed funding round to develop hardware for superconducting quantum computers here in Finland. And of course, this is not a Financial Times article, so we are not maybe there yet at this level of awareness, but this shows that it's actually possible to create a big movement out of Europe. So for the rest of my time, I want to tell you a little bit how this worked out, what was our path to get there, our little story, how I see the European quantum industry, how it's set up, and maybe a small vision on what's next. This is my personal view. So let's start with our story. Of course, if you are founding something, you need to have a visionary idea. And in our case, this is large-scale quantum computing. But of course, there are many other important technologies in the quantum world as well, like quantum sensing and so forth. But since my background is quantum computing, I will focus a little bit on this story. So what we have developed here in Helsinki with Aalto University, with VTT, is the technology for superconducting quantum bits. And actually, what you need to do is, if you are fundraising, you need to create a credible business case so that people are giving you money, and money in which they are committing into your story, not only to 1 or 2 years, but actually to 10 years or longer, because this is the time scale we are talking about here. So in our case, we were able to convince our investors that actually the technology for qubit reset, qubit readout, and so forth we have is valuable and it makes sense in investing. So this is the one important thing. The other important thing you need to have if you want to make a difference is you need to have a great team. So this is a picture taken a few weeks ago, meaning only 2 months after we have started the company, we were able to hire now today 21 people, 16 PhDs, 11 nationalities. So we really want to make a global effort, not focusing only here on Finland. Of course, we are based here, but on the long run, we want to be integrated into the whole European community, because you cannot do it alone. You have to do it as an ecosystem, as a big environment. So this is the high level, and of course there are many details in how to make this work. So you need to have the fundamental research, and the funding must go there and must continue to go there. This is what's happening. So the funders come from QCD Labs, which is one of the research groups at Aalto. In overall, it's the Quantum Technology Finland Center of Excellence that we have here. You need to have the enabling technologies, which is very important, because building superconducting quantum computers, it's not cheap. You need to have, for example, a big clean room, which we have here. You need to have partners like VTT, which enable this, which is very important. So this was very important. And of course, you need to have some initial funding, because to get there, you need to show credibility that actually people have believed in you in the past, so that the investors say, okay, it makes sense, let's continue this in the future. And you need to have, of course, the best talents. And here I put Aalto, which is very important, because Aalto, I think, is one of the universities which has now a quantum program for bachelor studies, and I think we need to have more of these activities as well in Europe, to have the talents in the future when the work needs to be done. In the business case, of course, you need to convince people that it's not basic science anymore, but that it's a deep technology that you can commercialize. And for this, for example, it helps you at least a lot if you have patents. And this is just taken from a recent Nature article, which shows the patent activity in quantum. You see China, United States, somewhere down here, United Kingdom. But this is something we really have to support much more in the future if you want to see such activities happen. Actually, Aalto is a very good example, because they help you as a researcher a lot to patent. But I've heard other stories in other countries where it's maybe not so easy. And this is something we need to be aware of if we want to protect our technology. You need to have a healthy ecosystem. I just brought 2 examples here. Blueforce, which is the market leader for cryogenics, which is a spin-out from Aalto. We have here Supercomputing Center, CSC, which are helping us in the background to get the computational aspect into it. And of course, you need also funding schemes which support the venture capitalists. And here we get actually a lot of funding from Business Finland, which is a funding organization helping you to commercialize technology out of the university into the industry. And then, of course, you need to have some entrepreneurs, which means in our case, scientists, which are willing to stop at least part of their scientific career and fully commit into the commercialization aspect of it. And of course, many of us are still scientists by heart and are maybe not willing to do this. So this is, of course, very important as well. And then when you start your business, what you need to do, of course, you need to build a product. We as a hardware company, we cannot do the full stack, so we are actively partnering, for example, with software companies, and we have a lot of quantum software here in Europe, which is actually great. You need to build partnerships also to the scientific community. So we are discussing, for example, with Open SuperQ people and QMix, which are two of the superconducting projects in the flagship. So this is very important because still this is where the magic happens, which is where the fundamental research is. And we want to bring this research into the industry. Now, this is something we are working on at the moment, the revenue streams. This, of course, will be important on the long run, but still you have to be aware that this is very early technology and you have to accept this. And then finally, of course, the team. But all of this together actually made it happen for us to build this strong effort, and we hope that together with this community, together with others from industry, we are really able to make a difference out of Europe. So how does the European industry look like? For me, in the beginning, it looked always something like this. So on the left-hand side, you have the universities doing the great research. You have enabling technologies like VTT and other organizations in Europe. And then on the very right-hand side, you have the end users, the big companies who want to use the technology. And what we need to do is we need to fill this gap in between somehow. And this is very important because it doesn't go directly from here to there. And of course, what others are doing, they're doing this approach, like the big names, Google, the Chinese, IBM. They just build the full stack. And unfortunately, this is not what we have here. And there was the question earlier, should we, for example, invest in machines, for example, provided by IBM and pay many million euros to have them locally, or should we do this ourselves? And I mean, for me as a European thinker, of course, we shouldn't do the first, but we should try to do it ourselves. And how do we do this? And is it even possible? I would say yes, because we are actually able to fill the stack. So we have leading hardware enablers in the cryogenics, we have cabling systems, electronics, all of this is there. It's European companies. You can go and buy it. You have different hardware approaches for the processors. So we are doing the superconducting approach. Still, we have companies doing the ion traps, the spin qubits. It's all there. You can just go and ask these people. And of course, in the end, you need to have the algorithms as well. And this is actually also where we are very strong in Europe. You just see it by the number of companies which are doing this, who are on different sides, on different stages of the software stack, providing these solutions. So it's all there. We just need to bring it together. And I think we as IQM, this is one of our goals, is be an integrator, talk to all of them, talk to the software people, talk to the end users, be a platform so that it's able to buy a European quantum computer. This is really our vision here. So how to make this vision happening? What's next? These are my final points. Of course, we need to collaborate. We cannot do it alone. We need to talk. We need to standardize. This needs to be mentioned, I think, much more often. There are no standards at the moment. We need to work on this. We need to integrate the different technologies. We need to create an industrial ecosystem. So the big companies, we need to talk to the decision makers there, not only the scientists, really the people who are making the decisions in the big companies to create awareness. This is what needs to be happening in the background a lot. Something that should be mentioned always is teach the next generation. We need more quantum physicists, more engineers. We need to teach physicists how to do the engineering. We need to teach engineers how to do the quantum, to have the critical mass available. And then, of course, we have to think big. If we want to compete globally, we need to think big, but still we should stick to the promises. We shouldn't oversell our stuff. We should tell the real time scales that the time that it will take, not make promises which we are not going to hold in the end. And finally, think a little bit outside the box. Talk to people who are not from this field, maybe from others. Talk to media, talk to journalists, talk to teachers, make all of this happen. And I think we are on a good track as a European group of researchers, politicians, industrials. We only need to bring everything together, maybe through events like this. And this is why I'm very happy to be here, talk today, and I'm happy to take any questions if there's time.
Thanks a lot. There is indeed time for a few questions. Please.
My question is about entrepreneurship. So what is done to train the entrepreneur to know what to do when they come from academia with an idea, to know what to do to sell it, to create startup companies, and eventually to become a larger enterprise?
So I cannot answer it for your case, but I know in Aalto, for example, we have an innovation center which supports such activities. They offer training courses. You can go and talk to them, but it depends, of course, on the university where you're coming from. I don't know if all of the universities offers them, but then I think you need to have a good network. And in our case, for example, all of the founders are scientists. We don't have any entrepreneurial background. So right from the beginning, we were talking to people from the VC world, from the entrepreneurial world, listening to them, trusting in them, so you need to find the right people, and then also to kind of accept that there are fields which maybe as a physicist you don't know so well, so accept what they are saying and trust what they do.
Please.
Thank you, Jan. A nice talk. Can you please clarify a little bit more what you are in principle offering with your company? Is it the processor? Is it, can you please elaborate more on that?
Yeah, so I didn't talk about this in so much detail because I didn't want to use it at an advertising session here, but more as my view of industry. So what we are doing is we are building the superconducting processors, so the qubit chips. We are integrating them, so we are building all the hardware that you need to assemble it in your fridge. We are not building the fridges and these things yourself. There we are using commercially available technologies, but then we are developing also on the electronic and control side, up to a level in the software where we can actually partner up with software companies, for example, for control and for algorithm. So we are really focusing on the hardware for the superconducting circuits, and they are basically the full stack, except for the cryogenics.
We have another one here. Oh, there was, okay, so we come to you, Tony, afterwards.
Hello, Meri Helle from Summa Semiconductor. I think excellent talk, thank you very much. I think we should really engage the young people and get more engineers and more scientists into the field. But I think it's really a challenge, and how can we make aware of this great science and this great technology. And the young people, they just see Google and Microsoft and all the software companies, but all of this is enabled by hardware. And how should we do it? Should we start opening the phones and seeing what is in there? Because it's really a miracle that it works. It's really amazing.
It's a good point, and of course a tricky question. Just maybe an example which comes to my mind. This hardware is built in Micronova, the clean room. I think last year or this year there was a high school opening right in front. So I think we should really start at this level in the schools. We need to create awareness that it's tech, it's math, it's these kind of subjects, and people have to be educated there, because if they don't studying physics or maths or so, after all, we have lost them already. So we should really start, I think, as a much earlier stage in schools or maybe even in kindergarten, create awareness how cool this stuff is.
Please. And then the last one here.
Thank you very much for your talk, Tony Apollago from Malta. I was wondering about the strategy, because often the quantum processor is seen as a race. But if one wins a race, the first one may not win, actually. It may win the second one, because achieving 50 or 80, then scalability becomes maybe not the platform for having 100 or 200. What do you think about the different platforms using for building a quantum processor, and what is your strategic vision of IQM in saying it's better not to win the, I don't like the sentence, not to win the battle, but to win the war? Even, I don't like but the sentence, it's too military.
Yeah, so I'm not a big friend either of the word race and these things. So of course, I mean, we are trusting in superconducting circuits. This is what we are doing. I think it's hard to say which will be the technology in 20 or 50 years, because we probably don't even know it yet. And yes, there are still different technologies out there, like the ion traps. What I think that in the near future, maybe there are certain problems which are running better on the ion traps, and other problems are running better on the superconducting machines, until we really have a full-scale, fault-tolerant, error-corrected machine. And for me, it's hard to say which will be in 20 years or so really the technology, and I guess we don't know it yet.
So we have a very last half question, please.
Really a half question. Edith Herzog from Giant in this case, and I was so much liked your last picture with all the key enabling technologies we have in Europe, and I was just hoping that you will show also the key enabling services, because I'm quite sure that all the 21 colleagues you have using, for instance, eduroam services and connectivity and trust and identity services will be a basic key enabling services. So beside the key enabling technologies, what do you think about the services you need?
Well, of course, I mean, still it's a company business, so you need HR, you need public relations, you need services. So I think, okay, it's not on the slide. Please, this is why I put this here. I was quite sure that I forgot many things. So please write me a mail. I will add it there. I think it's very important that we have the whole ecosystem in there, including the services. There are also consultancies and other things. I think everything is important, yeah.
So thank you very much again. It's by now clear that Finland can be very proud of its quantum ecosystem. And still there are, well, actually, I follow the advice of our hierarchy here, so I didn't check on my cell phone whether we have 26 more or 27 more member states of the European Union at this stage. So I'm not sure, but certainly many of those are represented in Quantera, the consortium of funding agencies which are supporting quantum technologies. And we are very happy that we have Silvia Kostka today here, who is coordinating that whole undertaking, which is very complex, so she will tell us everything about that now. Thank you.
Thank you very much. Good afternoon. So thank you very much for the invitation, although I know I'm competing here with the coffee break, so I'll be brief, no worries. So my name is Silvia Kostka, and together with Professor Konrad Banaszek, we coordinate Quantera. Quantera is the world's largest program of the research funding organizations in quantum technologies, and it is co-funded by the European Commission. So the main message of my presentation is that actually when it comes to the alignment of the policies in quantum technologies, within the last few years, we made an outstanding progress as Europe. So actually, the European landscape in quantum technology policies has become broader and much more diversified. So especially at the national and European level. The question is actually what we can do to keep the momentum going. As you can see here, these are quantum technology research funding organizations within the Quantera. And quantum domain is actually a very good example of the strategic cooperation within the European research area. In last few years, actually in 3 years' time, the European research community, European Commission, countries, member states, funding agencies and ministries were able to build multi-layer connections at the national, regional and European level. So I will focus on the last one, on the European level, because actually this is the most demanding one and the most challenging and the crucial one, obviously, if we want to be competitive still. The domino effect started in 2016 by Quantum Manifesto, then Quantera, and eventually with the Quantum Technology Flagship Initiative. These were very clear directions for member states to build their national agendas, their national policies in quantum technologies. So many of these are still in progress. Within the Quantera, we have this task that we map actually the developments of public policies in Europe. And every year we ask our partners what have been done so far and what are the developments. So according to our inventories, not only national programs of the usual suspects like UK, Netherlands or Switzerland has been carried on, but also the widening countries and the smaller countries are very active in the field. This is crucial in order to broaden the area, and this is very important to make the quantum technologies broader in Europe. So, as I said, this is very promising, and we are evolving, but what we can do to keep the momentum going? So, first of all, in Quantera, which is the part of the ecosystem responsible for research funding, we fund excellent transnational research projects in quantum technologies. This is crucial. So we pool national and EU resources through co-fund mechanism. We map development in public policies. We aim to foster the cooperation between academia and industry, and we spread the excellence across the era. It was a lot about, in the previous talk, about the team working. So you can see here that this is the team after the first call. Right now, the team is much bigger after the second call. We are honored to be advised by these excellence and fantastic researchers and industry representatives, which are the Strategic Advisory Board of Quantera. In less than 3 years' time, we managed to gather 45 million euros in order to fund about 40 transnational research projects. So about 200 research teams from 25 countries. This is really an impact. And we made it in a quantum communication, simulation, computing, information sciences, metrology sensing, and imaging. In call 2017, there was 221 pre-proposals, and this contributed to the quantum technology flagship. Later on, in the call 2019, a non-foreseen call, which was actually an action of only the partners of Quantera without the EC co-funded, we managed to fund another 12 projects. So here you can see the connections, the research teams within Europe, and how Quantera helps to build those within the Quantum Flagship. This is the core, so actually the projects that we are funding. In the call 2017, there was over 32 million euros coming, 11 from the European Commission, less from the member states, the next part. And within the second call, for about 30 million euros, we managed to recommend for funding another 12 projects. Obviously, we must ensure sustainability, and we will apply for the Quantera 2 program within the FED flagship call in Horizon 2020. And we aim at the next co-funded call in 2021, at the end of 2021, and this should be the biggest co-funded call ever, with hopefully the EC contribution of 15 million euros and Quantera's expected contribution at the level of around 30 million euros. We want to organize another calls as we did in the first round. So in the second round, we want to organize the biggest co-funded call and then call a non-co-funded call in 2023. So coming back to research policies. Although there are still major disparities between countries and regions, there are very strong driving forces, like, for example, the QCI initiative in Europe, that help us to overcome the fragmentation issue in Europe. We face it in Quantera, so we know how difficult it is when it comes to the 30 funders with different laws, different procedures, different research funding systems, and different priorities. But this is possible to overcome, and I'm sure that we can do it. But to keep the momentum going, what we need are two factors. First is the engagement. In every of the previous presentations, you have heard how important the cooperation is. This is crucial. So the engagement first, and then comes the funding. Funding is crucial here because we need, in order to achieve all the goals of the quantum technology flagship, we need to scale up. We need to scale up as the member states, as the partners of Quantera. We need to contribute to these goals in order to fund excellent projects, in order to fund them more, because they are fantastic. And just just to conclude, I would like to refer to Professor Mlynek's remark, who said, like, in his presentation, be generous. So please be generous, because lack of funding cannot be an excuse when it comes to such a big project. So, last but not least, about the engagement, we asked our partners whether they would like to contribute to the cooperation in future, and out of 30 organizations, there was not even one negative answer. So the engagement is there. What we need more is funding, and I will take also this opportunity to invite you all to Granada, where you will have a chance to listen to the project leaders that will present their works in November. Thank you very much, and have a great coffee break.
Thanks a lot. Well, they are generous, because actually this was the first call of the flagship before the flagship even started that they did. And then they said, no, it's not enough, it's not enough.
Yeah.
The Commission is not paying, let's do another one, okay? So this is really, they have a momentum which is really, amazing, and it was really a foundation for all these big initiatives. So maybe there is time for a quarter question before the coffee break. Or maybe there are many questions, someone is saying. Or maybe there is really growling stomachs and thirst for coffee, which is understandable after such an intense and rich session. So, well, enjoy your coffee. Thanks again, Silvia. Thanks to all the speakers. And we reconvene at 4 o'clock.